Alright, Internet, welcome back. So, fingers crossed that this audio is better than the last video's audio. I tested it, so we should be good. But if not, low expectations. That's a life lesson for you. Set your expectations really low, and you'll never be disappointed. Alright, motorbike. So, motorbike is an interesting one. And it's a very straightforward explanation. There's not a lot here to explain. And I would say this one is slightly easier. You can see this is a 6, not a 7, like the last one. And what we would need to do here is basically apply a self-destruct to the engine contract, and then we'll basically make the motorbike contract unusable. And what's happening here is we're using another proxy contract, so you can see there's some proxy stuff mentioned down here. We'll talk more about that later on. One really great thing about this specific challenge is they provided a lot of useful links to read through. So I highly recommend reading through each one of these and also reading into a series of other resources that I'll share with you that gives you a good idea of specifically what type of proxy pattern that we're going to interact with is, and also some of the weaknesses associated to it and the reason that it exists and the benefits of having a pattern like this. So each one of these links are relevant, and we'll talk about each one of these as we go through this. Now, the source code is lengthier, but not as lengthy as the one that we discussed previously, so it shouldn't take us too long to get through. So that is the challenge, is basically to self-destruct the engine contract, which is here, which will make this contract, motorbike, unusable. That's the goal. Now, let's go to our notes. We can see that this is self-destruct, so it's just a big bomb. It's going to explode. The solutions that I found, there are a few solutions I found, but these are the two that I found most useful. First off, another video from Digibard. I think it's Digibard or Digiboard? Digibard. So definitely check out his video. He does another great job at explaining the logical thought process of working through each of the pieces of the code and kind of how one would want to consider the weaknesses inside of it. So I think the way he explains things is quite interesting when it comes to the logical flow of the contract. So that's a good one. And my favorite resource would be Naveen Sahu again, which is here. So they've done another really great job at explaining specifically what the weaknesses are and how to exploit it. And this is what I'm going to use here for my solution. And I recommend going there and checking out this blog specifically to see how he explains it. So those are two good resources. There's tons of other links I'm going to walk you through, but those are the two resources I wanted to touch on. The next piece I think we'll discuss is going to be the proxy pattern we're going to interact with. So before I go into the code specifically, I want you to get a high-level view of what we're explaining here, so it hopefully is more easily digestible. So when looking at this pattern, historically we've used, I think it's a transparent proxy pattern, but what we're using here in this iteration is a universal upgradable proxy standard. So this is a new type of proxy pattern that was launched, I think, in 2021. This link here actually takes you to that EIP, the explanation of the storage layout, which I'll go to in a second. The purpose of this pattern and why they've launched it is basically to make it more gas efficient, and that's going to come down to where does the upgradable implementation or the upgradable function sit, and then also it helps prevent against storage collisions with basically where the contract is consistently stored. So this is slightly blurry, but it's the clearest one I could find. And it basically walks you through a high-level view of what you're looking at. So here you have your user on the client. They're going to interact with the proxy. So this is our proxy contract. This is our logic contract. Now the interesting thing about this is that the storage structure is going to be identical for where the logic contract sits. Logic contract is always going to sit in the same location, which we'll discuss up here in this EIP. And that's different from previous things. So previously there was always a storage collision, or there was potentially a storage collision due to the fact that the upgradable proxy contract would have, slot 0, 1, and 2 have A, B, and C, and then this one could have B, C, and A, and then there would be a collision because the variables aren't one for one lined up for the slot locations. Now, that's kind of a high level of what's happening here. Below here is showing you kind of how this can be hacked, so we'll walk into that in a second, but first let's go to this EIP to show you specifically what I'm talking about. So in the EIP, you can see here in the abstract, and I recommend reading this entire thing. It's not very long. It won't take you very long. You can see that basically it mentions that we're going to avoid clashes of storage because the logical contract is going to be stored at this location for that specific instance of that contract for all of the patterns that use this type of pattern. It's going to be stored in this location. And then you can go to this location to find out where that address is, which is what we're going to do later on. So that's how they avoid storage collisions. The other reason why this saves gas, and I think this is why it saves gas, is traditionally, when we looked at this last time, the upgradable function for the contract last time that we looked at for the transparency pattern actually sat within the proxy. So we had, if we wanted to upgrade something, we would call the function here that would have the upgrade piece, and that would then upgrade to a new address for where the new logical contract is sitting. So this could be L2 and this could be L1. But now, inside of this new pattern, instead of it being that way, the logic contract actually has the upgrade function inside of it, where in here it then points to a new version of itself. So this would be L1, this could be L2, and then this is going to say I want to call an upgrade and I want to point this to this L2, and then it'll then point this proxy to this L2 and then kill itself off, and then look at this one now. So it's interesting how they've moved that upgrade function to the logic instead of the proxy, and apparently that saves some gas. So that's the pattern that we're going to use here, and that's what we're interacting with. So I think that's good for now, and we'll go to the rest later after we've reviewed the code. So we have our code here, and I think that's too big, so we'll go to this size, and we'll start walking through it. So at the top here, we can see we have our compiler, which is 7.0, and I think it's greater than or less than, or is it greater than or less than? I think it's less than 7.0, greater than? I forgot which is which. All right, so import, we're going to import address.sol and initializable. So initializable is relevant for the proxy pattern we're using, and you'll see how that's used later on. So our contract motorbike, remember the motorbike is going to be the proxy contract. So this is just where data is stored, some data, and then the rest of it is just a straight up delegate call to the engine. Most of what you're going to see in this contract is just delegating to the engine. So this first variable here is a constant, and it's internal, and this is where the logic contract sits. And you can see this comment that was baked into the contract when we copied and pasted it. So it's putting it into this variable, which is implementation slot, and you can see it's all caps, which means in the kind of the syntax and the grammar of Solidity, usually when you have a constant variable, it should be all caps like this. And you can see that location that we saw in the EIP is right here. So that's where this implementation is going to sit for the logic contract. We have a struct for the address slot, which has some values for addresses. We have a constructor, and this constructor is basically going to take that implementation location where we want to interact with here, and it's going to do a few things. So first, it's going to require that the logic actually is a contract, so it's going to check that it's a contract at the address that's in this struct here. And then after we do that, we're going to then take that logic, we're going to add that value to this slot of get address, and we are going to then do the delegate call. So we're going to say we want to call on this logic variable, and we want to encode this initialization function, which is going to be down in the engine contract. We'll explain that later. And then we want to require success. So after that, we're going to come down to this delegate piece. So this delegate function here is going to call this implementation, and it's an internal value. And there's some magical assembly happening here. So for this magical assembly happening here, I actually had to do one-off searches for everything. And the reason I had to do that is because I didn't understand some of these things that were called out here. So I didn't really understand what called data copy did, return data copy did, or some of the other items here. So I had to do some Googling, and that's when I added these comments here, which will basically walk you through what the assembly is doing. So first things first is call data copy is basically taking a certain amount of bytes from location, or a certain, so this is basically the bytes S from call data position at F, which is going to be storage. So it's going to be stored here, and then it's going to take it to memory of position T. So this is going to be the memory piece. So T is memory, F is storage, and S is going to be the data that you're moving from location to location. So here it's going to say, okay, the call data, it's going to check that call data, that's where it is. We're going to then take it from this location and move it to this location like that. So that's what the copy piece is happening here. You can see there's delegate call. So this delegate call has a series of variables as well. So we can see this first one is basically the gas, the amount of gas you want to use. Basically the address that it's calling to, the amount of value that's being sent, and then this call data size is basically the same as this one. So we're getting the data from there. And then the 0 here is what's going in, and this is what's going out. So like I said, this is all commented here, and the reason I understand, or kind of a general understanding of what's being said here, is in my notes, you'll see down here that I went to the documentation, and in the documentation here, they actually walk you through what all those variables mean. So you can see these different instructions here. So if you just do a control find, you'll see that there's call data copy, which walks you through specifically what that is. You have a few other things. So we have return data copy, which is another thing that we discussed. It's the same thing, but you're returning the data. There's a few other things here. So you can see there's a call, which is basically directly related to delegate call. So we can just take this explanation and then copy it onto this. So looking through that table kind of helps me interpret what's happening here. But all in all, what's happening is basically we're just going to copy the data and apply it to this result, take any return data, and as long as the return data isn't 0, then we'll default to what it should be, and then we're going to return that back instead of reverting. So long story short, lots of Googling to understand that. The next piece here is a fallback function. So inside of this fallback function, basically, if none of these functions are directly mentioned when it's called directly, this fallback is going to kick in, like we've always talked about in the past. And when this kicks in, this is one of the only external functions that we have access to. And what's going to happen is it's going to take the implementation, slot that value, and then it's going to delegate it. So it's just going to delegate it to the engine. That's what's happening here. Below here, we have a get address slot. Now, the get address slot is basically going to find out where that address is. It's going to pull it back. So you can see the bytes 32 of the slot, pure returns, and it's going to return the address slot storage. So it's going to take that slot and apply it to this variable here, inline assembly. All right, so that's really short kind of contract. That's all of the gist of this contract is to delegate everything to the engine so the engine can take care of everything. The engine is where really kind of where all the magic happens. So we can see here we have our engine, and it's inheriting a lot of the methods from initializable, which is associated to that proxy pattern that we've just discussed. Here we have the slot location, as we've already talked about, so we'll skip past this. We have two state variables, so one is the address for the upgrader, and then one is the unit value for horsepower for our engine. We need to take this over so we can do some stuff below, but you'll see that in a second. We have our address slots again, we've discussed that already. We have our function initialize. So the initialize function here is what was called up earlier. So remember how I said we're going to come down here, we're going to call that. So the initialize basically has a modifier. So this modifier is being inherited from initializable. And this is basically a modifier that allows you to actually kind of deploy the contract. So the initialize piece here, this is, so you can see I put a note here, basically this is the constructor of this logic contract. Reason we're unable to use this is the constructor specifically is because it's already being used by the proxy contract above. So we have to add another variant to this called initialize. And you'll see in a second that this is actually where the big flaw comes in. I've added this note here. And the reason this is the mistake and this is the exploit that we're going to take advantage of is that this actually isn't initialized when it's initially deployed. So when the proxy contract's deployed, they don't immediately initialize this logic contract. And when you don't do that, that allows attackers to actually initialize it themselves. And for us, we're actually going to be able to take advantage of this and become the upgrader and then point this to an attack contract that'll explode everything. So that's where the weakness comes into play. But we'll keep going through this. So we can see the horsepower, if it was initialized correctly, would have been 1,000, and then the person that deployed the original contract of the proxy would have been the upgrader here. Then we have this upgrade to call. So this is basically being inherited from the initializable as well. And now this is what it's going to do is it's going to point this logic contract to the next one. So remember how we discussed we have L1 and then we have L2. So this upgrade to call is going to point this L1 to L2 so we can then change the logic contract and upgrade it to the next one. And that's what's going to happen here where we basically say this is the new implementation, this is the data we want to send, and then we have to pass this authorize upgrade function. So we'll jump down here real quickly. And this authorize upgrade is basically a helper function ensuring that only the upgrader can run this function here. So that's why we have to become the upgrader so we can actually point this to the bomb contract we want to deploy. So once we pass this, we can see that the upgrade call is basically going to take, point this to the new implementation with the data that we've asked it to point to and interact with. So those are those pieces. And we have another upgrade to call, which is interesting. I wonder, okay, I got it. So this is the upgrade call we're going to interact with. This is the upgrade to call the internal function that's going to actually do the upgrading and pointing to the contract as we needed to do. So you can see, I think this is a syntax thing. So when you see an underscore before the function, this is usually, I think, labeled as an internal function. That's a helper function for other functions to do things. So we can see that we have an address for the new implementation that we're going to put into here. And we have the memory data, which we're going to put in here. And we have the, yeah, you can see this is internal. It's labeled as internal. And then we have some stuff that's going to happen here. So we have another helper function, so set implementation, which is going to be down here. So we'll discuss that in a second. But we're basically going to put that new implementation here, and it's going to say, okay, as long as the data is greater than 0, so it actually has information inside of it, and it's a contract, then we want you to delegate call data to that new implementation, and we need to require a success to return. So this is basically saying we're going to push all the information, we're going to delegate the call to that new implementation so they can take over. Our set implementation here is going to take the new implementation. It's going to ensure that it actually is a contract that we're deploying it or pointing to. And then we have some inline assembly. So it's going to basically take the variable R into this variable. Inline assembly is going to take that implementation slot and it's going to add it to this. And the new implementation is going to be the value for that slot. So we're basically, in this inline assembly, what we're doing is we're going to update this value here with our new address and that new slot for that specific type of pattern. And that is the whole contract. Look at us being efficient. Feels so good, doesn't it? All right, so we've talked about all this and we've talked about that. So before we execute this, I'll quickly show you a high-level understanding of what's happening here and how we're going to hack it. So this is an image I got from Google. Not really sure kind of what it's related to, but I have the blog here, so if you want to go read the blog, feel free. All right, so this is basically showing you how this attack kind of happens at a high level. So here we have our proxy contract. So you can see this is our proxy contract that has our data, and then our logical contract. This is, say this is our L1, and this is going to be our malicious L2. And we have a series of other proxies that are interacting with this proxy. This is just kind of a different type of implementation of this. So we have our user, our poor user that's about to get pwned, and our attacker here that looks like a dope frog. And what they're going to do here is they're first going to basically become the upgrader so they can then initialize this contract. So as soon as they become the upgrader, they can initialize the contract. And when they do that, when they initialize this, they're then going to point this new contract to our malicious L2, which encompasses a self-destruct, will then eventually actually explode everything. So when it explodes, it's not going to explode that. Let me take that back. So when we explode this, we're going to explode the implementation. When we explode the implementation, then the proxy contract becomes useless. The Motorbike no longer works because we destroyed the engine. And the reason that is because remember, inside of the implementation is the actual upgrade function. So if we destroy the upgrade function, we can no longer upgrade. It's no longer useful. So we have to redeploy the entire contract to get it to work again. And that's what's going to happen here. So with that being stated, let's actually hack this contract. So when we open this up, we do an await contract ABI, you'll see that the only thing that we can see are the 2 bits inside of the Motorbike. So inside of the Motorbike, we can see the constructor. You can see it's a constructor here and the inputs that are coming in. So it's going to be the logic that we're pointing to originally. And then the other thing we can see here is going to be the fallback function, which we've already talked about. So this is the only one that's external. And we can see that it basically, this fallback function is going to point to the implementation and delegate whatever. So that's what we can see. But we want to get access to this engine because we need to become the upgrader and take all of that stuff over. And the way we can do that is by actually finding the address inside of this slot here. And to do that, we're going to follow some instructions from this block here. And I've actually written out the logic flow here to kind of walk you through specifically what we're trying to achieve. But I've already kind of walked you through most of that. So really we need to gain access to the engine. We need to become the upgrader via calling initialize. Then we need to set up the bomb, and then we need to call the bomb. That's what's going to happen with this logical flow. So if we open up this here, we'll pull this out so we can have them side by side. And I'll walk you through some of this code that we're going to put in here. So let's make this bigger. And we can see, if you do a good old copy and paste, what's happening here is we're going to do find out what the address is. So we're gonna use Web3.js. We're gonna get storage at. This is something we've used in the past. We're gonna say, okay, this contract, we want to see what's sitting at this slot in this storage. What's at this storage location, and then it's gonna then pop out the value that's in there, and we can see that that value is gonna be the address of our L1, our engine. That's where we're trying to get to our engine, and we've put this inside of this variable. So now that we have that, we want to basically slice off those zeros. So what this is doing is basically, you can see it's cut out these first 20 zeros. What it's saying is I want to slice off the last 40 and then get rid of the remaining 20 and then concatenate it against this 0x. So that's going to give us the actual address that we care about. And we're going to put that into a variable we can use later on. So once we've done this, now we want to go through the process of figuring out the four bytes of initialize in our engine. Because after we've done this, we've gotten our address. We need to figure out specifically in this address what is the first 4 byte signature of that function that we need to call. And then once we've gotten that, then we'll call it. And you can see what's happening here is we're going to say we want to send a transaction from player to this implementation address that we just found. And then we want to send the initialized data variable here to interact with the initialize. Because remember, when we call initialize, let's go back here to reignite our brains. So here, remember, when we call initialize, it's going to allow us to be the sender. And the reason it's going to allow us to do that is because it wasn't initially set up when it should have been, and it's going to allow us to do this because this is going to be false instead of true. All right, that is OBS, not what I wanted to see. All right, that's set up. So now we're going to figure out the first 4 characters of upgrader for that function. And then we're going to put that into a variable, and we're going to error it out. And the reason this errored out is this happened to me as well, is instead of saying upgrade data, which is a variable we care about, it says upgrade sig. So we just need to change this to data. And that's true. So what this is saying is basically we've found this the signature for the first 4 bytes of this function. We check to see if we are actually the upgrader. So here what we're doing is we're going to call that. We're going to say from player to this address. I want to call this item, and I want to see if it matches the player address, all lowercase, in comparison to who the upgrader is, and it says true. So that lets us know that we've officially become the upgrader, which is great. So now we have to deploy our bomb engine. So I already have this in Remix set up, so we can have our bomb engine here set up, and it's basically going to do self-destruct, and it's going to send it to a bogus address and destroy everything. So if we save this and compile it, it's all good. We're going to deploy this to inject web3, and we're going to deploy that. And as that's doing its thing, we'll go to the next phase. And okay, we did that. We deployed. So then we have to go through a few steps to set up our contract to allow us to interact with the bomb we just deployed. So first things first is we need to get our bomb address, right? So we need to replace this with the address we just deployed in Remix. And that's going to be this here. So we will add that to that variable of bomb address. We're then going to get the first 4 characters, the signature of that function we just set up. So you can see in Remix, we set up this function here called explode. We need to get that into its basically encoded function signature so we can interact with it. We're then going to basically get the information from the upgrade signature. So the upgrade to call function that we discussed earlier. We need to get this, so we're going to take the name, it's a function, we're going to get the inputs, so we know that the new implementation is going to be our attacker address, and it's going to take in bytes data as well. And then we're going to add those together into an array. So we've just put basically our bomb address here, and we put the first 4 signatures, signature of explode together, so we can then concatenate that all together to send off to the upgrade data. So this variable here, upgrade data, basically includes an encoded function call of the upgrade signature. So that's going to be this information here, the upgrade call. That's allowing us to point L1 to L2. So that's going to go here. We're going to input our address, which is going to be this. And we're going to input our bytes data, which is going to be this, the function we want to interact with, which is the bomb exploding. And that's all going to be concatenated into here. So we can see this is our address here. And then the first 4 bytes has been disappeared into something convoluted. Oh no, you can see it here. So 8B3BC. So that's going to be our signature there. And then this signature here, the add to call is going to be this piece here. So that's kind of all of it concatenated together into a single bit of data that we can send into our transaction. And if we input that here and we deploy this, we'll see that in this send transaction, we said from player to our implemented address, which is going to be our attacker address, and then we wanted to, I don't know where to go. We wanted to put in our upgrade data, which is basically saying, I want you to interact with this address, I want you to hit explode, and I want you to make sure that you point the new address to this address, so when it hits explode, then everything goes poof. So after all of that stuff, this should have worked. We should have exploded the address. As this is loading, I want to show you some of the fixes here. So this is the previous vulnerability. I'll point you to this so you can read more about it. This talks you through a vulnerability that happened in the real world. Here is some good explanations to the pattern that we're talking about. So this is UUPS, and then this is the final fix. So the fix is basically to ensure that you're initializing this either via the constructor immediately as soon as the proxy contract is deployed, or when you deploy the proxy contract, you're immediately afterwards manually initializing the other contract. So you're initializing that logical contract when you're deploying it, so it's no longer not initialized, so the attacker can take advantage of that. So if we come back here, we can see that the level is completed. So congratulations, Ethernaut. Kudos to you. And I'll see you on the very last level, double entry point. So excited. Last level.